Hello everyone, let us start our 11th lecture, and this 11th lecture the topic will be, first we will solve one problem on nucleation rate, because in the last class we solved two problems and one more problem we will solve. We will just rather give you hint and you come up with the answer. And then the second one is basically how to determine the value of gamma SL, or rather a physical concept of interfacial energy. So, we will take this next two things after solving that problem. Let us first solve a problem. The problem statement says, in a phase transformation, it could be solid liquid or solid solid anything, but for the time being, let us consider it is a solid liquid transformation. Okay. And there the mentioned part is I is 10 to the power 6 per meter cube per second, as we have already discussed that what could be the unit of I. Unit of I is basically the number of nuclei, which is actually stable nuclei, per unit time, per unit volume. And this is at room temperature, this RT means room temperature, and del G star equal to 2.07 into the minus 19 joule, and gamma let us put it as SL, SL 0.05 joule per meter square. Calculate I when gamma SL increases by 10%. It means that the transformation temperature, which is the melting temperature, does not change, and it is also at room temperature. Now, let us only revisit some of the equations which you will be needing for solving this particular problem. First equation is I equal to I0 exponential minus del G star plus del G d by kT, and then del G x star is equal to 16 pi 3 gamma SL q by del G V square, and from I think these two equations would be sufficient to solve this problem. Now, since this is at the same temperature, we can assume that these part, if we break this one into two parts, I0 exponential minus del G star by kT exponential minus del G d by kT. So, these term would remain same when gamma SL is 0.05 joule per meter square, and at the same time when gamma SL increases by 10%. Now, we know that I equal to 10 to the power 6 meter minus meter square meter cube and per second. Now, before putting those values, we can do a little bit of adjustment to this particular equation. We can write that we are just giving hint, mind it, we are just giving hint. You have to solve it, you just do this exercise. We can take I1 when gamma SL equal to 0.05, and another one is I2 gamma SL equal to 1 point, it says 10%. So, 1.1 into 0.05. So, these two, if we take ratio, because since this part is same, we can get, and this is also same, this is a constant. So, now exponential minus del G star when gamma SL equal to 0.05 and divided by kT and exponential minus delta G star gamma when actually this I am putting as a superscript gamma SL equal to 1.1 into 0.05. Okay. So, this I am just indicating that this value we have to calculate when gamma SL equal to 0.05 and this value we have to calculate when gamma is equal to SL increases by 10% from the existing value. And interestingly, as we have mentioned that del HM does not change, as well as Tm does not change. Now, if we see this expression, this part actually does not change, because this part contains del Hm, del T, Tm, Vm. So, Vm for the metal, let us say this is a metal, pure metal. Tm does not change, Vm does not change, delta T remains same, because if Tm remains same and if we are taking it at room temperature, so del T would remain same. So, this one would not vary. The only thing that would vary is this one. Now, we can calculate what could be the value of gamma SL. Gamma SL is equal to 0.05 and when gamma SL increases by 10%, that time it would be 0.055 is basically joule per meter square, joule per meter square. Now, from that it is basically you can do little juggling and then can get to the value of I 2, because these part both the cases are same. You replace this T with the room temperature, let us say 25 degree Celsius, let us say room temperature equal to 25 degree Celsius, which is 298 Kelvin, K equal to K, which is the Boltzmann constant, is equal to 1.38 into 10 to the power minus 23 joule per mole per Kelvin. So, now you can get the value of this term, since we know delta G star also. So, delta G star is this. So, delta G star equal to 2.07 into 10 to the power minus 19. So, I take this equation, I know gamma SL, I can calculate this quantity. So, once I calculate this quantity, so then the problem becomes very simple, we can get the value of I 2. Now, you can, if you do this calculation, you will see that this I 2 value would decrease hugely, and you would get I 2 to the order of 10 to the power minus 2. So, now this is almost meter cube per meter cube second minus 1. So, this range, I am just talking about this range, you will get to this range. So, now you can see that if interfacial energy increases just by 10%, you decrease the I 2, which is the nucleation rate, hugely from 10 to the power 6 to 10 to the power minus 2. So, it is a huge decrease. So, that now you can realize that the importance of gamma SL on the nucleation kinetics, because it actually hinders the kinetics. These value, if you can later on you can also have a change in this delta GV value, you will see that if this one increases, this one would also increase, okay, because this one increases means it helps in nucleation. So, you can do that calculation, but first you try this calculation, you will see the difference, see the influence of this gamma S7. So, that is what we just discussed this problem, and later on with the TAs you can have discussion, and we can have also discussion with me. So, we can discuss over email transactions, the way we communicate in this course. Now, let us come back to this part. Okay, we will give you many other problems on this nucleation rate itself. You will solve it and then interact with the TAs. Now, coming to the next part, which is how to determine the value of gamma SL, or rather the physical concept of interfacial energy. From that problem, it is pretty clear that the interfacial energy is acting against the nucleation kinetics. Now, we have to see why it acts against to that nucleation kinetics. Now, while we would like to quantify, because we have quantified delta GV very easily, delta GV we have quantified very easily, because it is pretty simple expression Vm, and we have also seen how easily we can get to this particular formula, and we can calculate this. But it is not that easy to calculate gamma SL or the interfacial energy. Interfacial energy is extremely critical in phase transformation, at the same time it is very difficult to find. Now, in order to find interfacial energy, since we have experienced in our discussion that it gives a sense that if this is an interface and if we consider a regular array of atoms, so let us say these are the atoms which are connecting across an interface. Let us say this interface was not there. Now, once I put interface, I have to somehow disturb these bonds, and some cases these bonds will be broken. These bonds will be broken. Once I break these bonds, in order to break this bond, I have to send energy, I have to give energy to break this bond, because these bonds are very strongly, these atoms are very strongly attached. Now, whenever I break these bonds, that means it creates a positive energy on this surface. Okay? So, it is not very easy to break these bonds. Now, where from we get this concept that the bonds are broken? Now, let us say any surface of a metal, any surface of a metal. So, now one surface is solid surface, the other surface if we consider it is basically atmosphere or the vapor. Okay. So, we can say that, and that here we have solids, all the atoms are regularly arranged, but across this interface there is no atom of that particular solid. So, though we have vapor pressure, some atoms will be there, but from our experience we have seen that physical existence is not there, because in the naked eye we cannot see this. This surface has a positive energy. So, we call it surface energy. Similarly, in the, see this is solid vapor where the bonds are absolutely broken, but in case of liquid, solid liquid, the bonds are not completely broken. Okay. So, in the solid liquid case, if there are, let us say initially there are all liquid, all solid initially, let us say, now it starts melting. Okay. So, when it melts, these atoms moves little bit and disturbs the atomic arrangement around this region, and once it disturbs the atomic arrangement, these bonds either get broken or get distorted. So, both the cases we need to send sufficient energy. So, this energy is coming as a positive energy, and that is getting stored as a surface energy. Okay, fine. So, now in order to, now you can see clearly that in order to have some sort of knowledge about the fundamentals, the physical aspects of this particular surface energy, we need to understand structure of the solid. Okay. Since we will be looking at more metals and alloys, and we have started with the single component metal solid liquid transformation. Now, let us only consider metal, and that too simple metal. We are not going to consider a very complicated metal. We will have lot of complicated metals, but we will not take that. We will simply take, for example, iron, because steel is important issue in our heat treatment course. We have copper, we have chromium, all those elements. Now, whenever we talk about the structure of metal, interestingly, in most of the common engineering metals, what we use, for example, iron, we use copper based alloy, we use nickel based superalloys, we use chromium as an addition to the iron, okay. Then we use aluminum. So, those are very commonly used metals. They have generally a simple structure. Those structures, you might have heard those names, either BCC or FCC. We have already seen that the BCC is body centered cubic, and this is face centered cubic. And whenever we talk about BCC, we have example of iron, and if it is pure iron, this BCC stays, if it is alpha, it stays up to 910 degrees Celsius, if it is pure iron. And now, FCC one example, and also there is an example of chromium. Chromium is BCC metal. Then FCC metal example, again I can give example of iron, where at that time it will be gamma, and in case of pure metal, it stays from 910 degrees Celsius to 1395 degrees Celsius. So, if it is a pure metal, we will come to that, how come these numbers are coming. Now, one more FCC metal example is copper. We will solve some problems using the data of copper, how to determine surface energy of copper from the bond energy data, and later on some problems will be there for you to solve on iron. Now, there is one more common structure we experience in our engineering alloys. One is FCC, HCP, which is hexagonal close pack structure. The examples are titanium based alloy, titanium, zirconium, hafnium. So, those are the alloys, but these two alloys are very commonly used. Of course, they are strategic alloys. For example, titanium based alloys, one great example is biomaterials. Okay. So, now, but we will concentrate our discussion on BCC just to get the concept of how to determine surface energy. Now, in order to do that, first we have to understand how these structures are formed. So, we will just have a quick look at how these structures are formed, though this course is not on the structures, but we will have a simple discussion, not very detailed discussion, rather a very short discussion, which will be sufficient for us to calculate surface energy. Whenever we talk about, let us say, a cubic system, whenever we talk about, let us say, crystal structures, in metals, we experience 3D or 3-dimensional array of atoms, and in most cases those atoms are very regular and they have translational symmetry as well as rotational symmetry. So, we are not looking at the symmetry part, but at least let us see how those you can find that there are if you go to a simple material science book, you will see that the structures there are mention of brevis lattice, and there are 14 brevis lattice, and these 14 brevis lattice are broadly segmented into 7 crystal systems, which are called cubic, then tetragonal, then orthorhombic, then rhombohedral, then hexagonal, monoclinic, and triclinic. So, these are 7 crystal systems, and we are looking at the cubic system. And in the cubic system, there are 3 brevis lattice. One is simple cubic, then body centered cubic, and then another one face centered cubic. Now, if we would like to see a simple cubic, so it is a regular cube. This is a regular cube, and there is a point at each corner position. So, it is a point, the lattice is basically a point. Now, it is a regular arrangement of points, and down if you indicate it by A, B and C, and in this case A equal to B equal to C, and if you see the angle, so this is let us say beta opposite to B, this is alpha, and let us say this is gamma. So, these are 3 angles that are being formed by 3 axes, orthogonal axes. So, that time alpha equal to beta equal to gamma equal to 90 degree. Similarly, if it is body centered cubic, the only difference is you have at the center of this particular cube, we have another point which forms BCC, and then this is BCC, where there is a point at the center of the cube, and then in case of FCC, the center point is not there. So, I am just drawing the FCC separately. And in this case, one point at each corner, that means 8 corners, and there is a point at the center of all 6 faces. So, this becomes face centered, which means the center of each face I have one more point. So, that becomes FCC. So, these are all arrangement of points. Now, in case of BCC, if we let us say put chromium atom at each lattice points, these are lattice points. So, that means chromium atom will be put here, here, so that time it becomes BCC crystal of chromium. Similarly, in case of FCC, if we let us say put copper at each lattice point. So, I am putting lattice points, all the copper atoms, then it becomes FCC crystal of copper. So, now if this becomes my lattice, where it is the arrangement of points, and then if we put bases, that means copper atoms, then it becomes a crystal. Now, once we have crystal, that means we have atoms now. Now, how those atoms are placed? We know that atoms are placed at each corner, but what would be the distance between the atoms? Now, these atoms are a sphere, and that to a solid sphere, and that to incompressible sphere. So, that means they cannot be compressed. And as per our convention, we say that these nearest atoms are bonded. This is first, and second is these nearest atoms are also joined. Okay? So, joined. Now, that means in case of simple cubic, all the atoms will be joining together. So, that means if we draw a simple cubic, so this is also connected. So, all the atoms are connected. So, that means one of the sides will be, if the radius, this is r is the radius of that sphere. So, that means 2r is basically A, which is the lattice parameter. So, that means in case of simple cubic, all the atoms are connected, and the distance between these two atoms would be simple, the center of these two atoms would be 2r, which is nothing but the lattice parameter. So, now you can see the lattice parameter of simple cubic system is nothing but addition of the radius of two sphere. So, let us stop here, and we will continue the same discussion in our next lecture. Thank you very much.